Imagine a universe, not so different from our own, yet strangely reversed. In this mirror world, stars gleam with an eerie glow, and planets shimmer with unfamiliar hues. This is the realm of antimatter, a concept that has captivated scientists and science fiction enthusiasts alike for decades. Antimatter, the enigmatic twin of ordinary matter, holds the key to unlocking some of the universe's most profound secrets. Antimatter is not just a figment of our imagination, it's a real phenomenon, as concrete as the ground beneath our feet. But instead of being made of atoms, the building blocks of everything we see and touch, antimatter is composed of antiparticles. These antiparticles are like the mirror images of ordinary particles, identical in mass but with opposite charges. The discovery of antimatter has revolutionized our understanding of the universe and challenged our perception of reality. It has opened up new avenues of exploration, leading us to question the very fabric of existence and the fundamental laws that govern the cosmos. In the heart of every atom lies a nucleus, a dense core orbited by tiny particles called electrons, which carry a negative charge. But what if we could reverse this arrangement, replacing electrons with their positively charged counterparts, positrons? This is precisely the essence of antimatter. Just as matter is composed of atoms, antimatter is made up of anti-atoms. For instance, a hydrogen atom, the simplest atom in the universe, consists of a single proton and a single electron. In contrast, an anti-hydrogen atom is made of an antiproton, a negatively charged particle, and a positron. When matter and antimatter collide, they annihilate each other in a spectacular release of energy, a phenomenon that has fueled countless science fiction stories. This annihilation process is not just a theoretical concept, it has been observed and studied in laboratories around the world. The study of antimatter offers a unique window into the fundamental symmetries of the universe, revealing a hidden duality that challenges our understanding of the very nature of existence. Antimatter, with its exotic properties, behaves in ways that often defy our everyday intuition. Its existence was first predicted in 1928 by physicist Paul Dirac, who was trying to reconcile quantum mechanics, the theory governing the microscopic world, with Einstein's theory of special relativity, which describes the behavior of objects moving at high speeds. Dirac's equations, which sought to describe the behavior of electrons moving at relativistic speeds, yielded a surprising result. They predicted the existence of particles with the same mass as electrons, but with opposite charge. This groundbreaking prediction was initially met with skepticism, but it wasn't long before experimental evidence confirmed the existence of these antimatter particles. In 1932, Carl Anderson, while studying cosmic rays, detected the signature of a positron, the antimatter counterpart of the electron, confirming Dirac's prediction. This discovery marked a turning point in our understanding of the universe, revealing that for every particle of matter, there exists an antiparticle with opposite charge. The properties of antimatter have been rigorously studied in laboratories, and we now know that antimatter particles have the same mass and spin as their corresponding matter particles but with opposite charges. For example, an antiproton has the same mass as a proton but carries a negative charge, while a positron has the same mass as an electron but carries a positive charge. If matter and antimatter annihilate each other upon contact, where does all the antimatter in the universe hide? This question has puzzled physicists for decades and remains one of the most significant unsolved mysteries in modern cosmology. The prevailing theory is that during the Big Bang, the event that marked the birth of our universe, equal amounts of matter and antimatter were created. However, for reasons that are still not fully understood, a slight asymmetry, a tiny imbalance in favor of matter, must have existed in the early universe. This minuscule imbalance, perhaps just one extra particle of matter for every billion pairs of matter and antimatter, had profound consequences. As the universe cooled and expanded, matter and antimatter annihilated each other, leaving behind a small surplus of matter, the matter that makes up the stars, planets, and galaxies we observe today. The search for this primordial antimatter is ongoing, with scientists looking for clues in cosmic rays, high-energy particles that bombard Earth from space, and in the faint afterglow of the Big Bang, known as the cosmic microwave background radiation. The universe is not static. It's a dynamic and ever-changing place where particles are constantly being created and destroyed in a cosmic dance of creation and annihilation. Antimatter, despite its elusive nature, plays a crucial role in this cosmic ballet. One of the most spectacular examples of this cosmic dance occurs in the hearts of stars, where nuclear fusion, the process that powers the stars, is constantly forging new elements from the ashes of spent ones. In these stellar furnaces, antimatter is routinely created as a byproduct of the nuclear reactions that fuel the star's immense energy output. For instance, in the core of our own sun, hydrogen atoms are constantly fusing to form helium, a process that releases tremendous amounts of energy in the form of light and heat. During this fusion process, positrons, the antimatter counterparts of electrons, are produced. These positrons don't last long, they quickly annihilate with electrons in the surrounding plasma, releasing energy in the form of gamma rays. These gamma rays, carrying the signature of matter-antimatter annihilation, can be detected by telescopes here on Earth, providing us with a glimpse into the fiery heart of our star. Harnessing the power of antimatter, a technological frontier. The immense energy released during matter-antimatter annihilation has captivated the imaginations of scientists and engineers, who envision a future where antimatter could fuel interstellar spaceships, power advanced medical devices, and revolutionize energy production. Antimatter is the most energy-dense substance known to exist. When matter and antimatter annihilate, they convert 100% of their mass into energy, making it a far more efficient fuel source than any existing technology. For comparison, nuclear fission, the process used in nuclear power plants, converts only about 0.1% of its mass into energy. However, harnessing the power of antimatter is a formidable challenge. Producing even minuscule amounts of antimatter requires enormous amounts of energy and sophisticated equipment. Currently, the world's most powerful particle accelerators can only produce a few nanograms of antimatter per year, and storing it is an even greater hurdle. Antimatter must be kept isolated from matter to prevent annihilation, which requires sophisticated magnetic traps that can suspend antimatter particles in a vacuum, preventing them from coming into contact with the walls of the container. Despite these challenges, the potential benefits of antimatter are too significant to ignore. Research and development continue, driven by the hope that one day antimatter will revolutionize our world. Antimatter in medicine. Revolutionizing healthcare. While the prospect of antimatter-powered spaceships may seem like a distant dream, antimatter is already making a tangible impact in our lives, particularly in the field of medicine, where it's being used to diagnose and treat a variety of diseases. One of the most well-established medical applications of antimatter is positron emission tomography, or PET scanning, a powerful imaging technique that allows doctors to peer inside the human body and visualize metabolic activity in real time. PET scans rely on the detection of gamma rays emitted during the annihilation of positrons, the antimatter counterparts of electrons, with electrons in the body. During a PET scan, a small amount of a radioactive tracer, which emits positrons as it decays, is injected into the patient's bloodstream. These positrons travel a short distance before encountering electrons in the surrounding tissue, resulting in annihilation and the emission of gamma rays. These gamma rays are detected by the PET scanner, which uses this information to create detailed three-dimensional images of the targeted organs and tissues. PET scans are invaluable tools for diagnosing a wide range of conditions, including cancer, heart disease, and neurological disorders. They allow doctors to detect and monitor tumors, assess blood flow to the heart, and study brain activity, providing crucial information for diagnosis and treatment planning. Unraveling the mysteries antimatter's role in cosmology. Antimatter is not just a curiosity, it's a fundamental constituent of the universe, and its study has profound implications for our understanding of the cosmos, from the earliest moments after the Big Bang to the evolution of galaxies. One of the most perplexing mysteries in cosmology is the apparent imbalance between matter and antimatter in the universe. As mentioned earlier, the Big Bang should have created equal amounts of matter and antimatter. However, our universe is predominantly made of matter, and the scarcity of antimatter remains one of the most significant unsolved problems in modern physics. Scientists believe that this matter-antimatter asymmetry, known as baryogenesis, must have arisen from subtle differences in the behavior of matter and antimatter particles in the extreme conditions of the early universe. These differences, however small, could have tipped the scales in favor of matter, leading to the universe we observe today. To unravel this mystery, physicists are conducting experiments at particle accelerators, recreating the extreme temperatures and densities that existed shortly after the Big Bang. By studying the interactions of matter and antimatter particles under these conditions, they hope to gain insights into the mechanisms that may have led to baryogenesis. A future fueled by antimatter, dreams of interstellar travel and beyond. The discovery of antimatter has sparked dreams of interstellar travel and a future where energy is abundant and clean. While these visions may seem like science fiction today, the pursuit of antimatter research continues to push the boundaries of our technological capabilities. Antimatter, with its unmatched energy density, holds the key to unlocking new forms of propulsion that could one day enable us to explore the cosmos at speeds previously unimaginable. Imagine spaceships powered by matter-antimatter annihilation, hurtling through the vast expanse of space at a significant fraction of the speed of light. While such concepts may seem like the stuff of Star Trek, the principles are grounded in reality. However, the engineering challenges associated with producing, storing, and utilizing antimatter on a scale necessary for interstellar travel are immense, and will likely require centuries of technological advancement to overcome. Nevertheless, the pursuit of antimatter research continues to inspire and challenge us, pushing the boundaries of our understanding of the universe and driving innovation in fields as diverse as medicine, energy, and space exploration. Antimatter, once a theoretical curiosity, has emerged as a tangible tool for scientific discovery and a beacon of hope for a future where the seemingly impossible might one day become possible.